Okay, so yeah, our second speaker on SLT today is Stuart Pearce from AEM, where he's a Senior Director of Field Marketing. So he's responsible for both field marketing and product management of AEM's semiconductor test instrumentation solutions, bringing disruptive and differentiated solutions to the semiconductor test space. Focus on application-specific test solutions, intelligent system level test, and burn-in for semiconductor and electronics companies serving high-performance computing, 5G, automotive, and AI markets. And he's going to give us an introduction to system level test. Over to you, Stuart.
Okay, thanks, Mike. Can everyone hear me okay?
Yeah, we can hear you and see your screen, so good to go.
Okay, perfect. Okay, so the first slide I'm just going to share is I know Jürgen just covered some of the industry trends, but I think there's a few points in this slide. I won't go through every one here. I think there are a few other key points that are important for system level test. Die complexity, Jürgen covered this, but the other aspect of die complexity isn't just the complexity of the die itself, it's also the development costs and the time to market trade-offs. With traditional test flows, it does take a long time to develop the test flows and get them optimized, ready for production, and that's just getting worse as the complexity of die and packaging technology increases, and system level test is a way to also assist in some of those challenges. Packaging, I think Jürgen covered well. The other area I just want to touch on briefly is the emerging thermal challenges. So not only are the design margins at the silicon level being eroded as we go to these lower newer process nodes, but also the thermal challenges that are occurring as we have more and more transistors operating in higher power devices. This is causing a lot of challenges from a packaging and test perspective in terms of managing the localization heating effects that are required to accurately characterize, debug, and validate working die in the end application. So thermal management is key and a big part of our system level test solutions. Our supply chain evolution is probably something outside of the scope of this particular session, but as we all in the semiconductor industry appreciate, it is a very complex supply chain that we've managed to create over the last few decades, and that is now being revisited and unraveled as we try to plan for the future. In terms of design tools, there's a lot of work going on in providing enhancements to EDA and design tools and links into test. Particularly, there's a lot of work being done with links into ATE. That's now beginning to evolve into looking at the life cycle management of silicon. So tools are now evolving at the ecosystem level for being able to help provide tools that will enable not just links into ATE, but also links into system level test and in-field monitoring. So this is an exciting area that is really beginning to enable the rest of the ecosystem now. Also, there's a lot of work going on in industry standards. The IEEE scan standards 1149 has been around for many, many years, and it was introduced probably 20 odd years ago to help reduce the cost of test. It's had a lot of limitations, and now it's being enhanced to support the much deeper scan chains that are required to test all the extra transistors and get data in and out of the chips at much higher speed. So there's a whole bunch of different emerging IEEE standards that people are beginning to take advantage of. SSN is another emerging standard to help manage the traffic within the device and some of the power management functionality. And at the system level, we're beginning to see the need for integration and running both BIST and SCAN whilst in the SLT environment for lifecycle and health monitoring. So these are all standards that are evolving that will further assist the ecosystem to further enable system level test as we move forward. The other big part of this is data collection and analytics. The industry has had for many years some standards with STDF. There's other emerging standards coming out of SIMI like RIT-DB that enables a much deeper data logging to have much more availability to analytics to help in some of the data analytics to further optimize test flows moving forward. So there's a lot of work going on not just in database standards for collecting the data, but also in tools becoming available for doing some of the data analytics to make some of the trade-off decisions of where to put your time and money in the test ecosystem, and we'll get into that a little bit more. For this presentation, the important part is more around the test flow changes. SLT is now required, and I've got slides on that we're going to cover. It's no longer a matter of should we do it, it's a matter of the industry really has started doing this in some of the verticals, and other verticals are beginning to embrace the system level test flow enhancements. So let's go on to the traditional test flow. So today the test flow is wafer probe, dice, various levels of burn-in, final test, and then system level test. This is the traditional serial test flow. And this may be a surprise for some people in the audience, but system level test isn't new. You know, the industry really started to adopt system level test back in the mid 2010s, particularly driven in the high performance computing area, where it just became more cost effective to system level test to get the extra mission critical defects out, whilst people continue to try and find ways to cost optimize the test flow and catch the same faults. System level test was found to be needed to catch those defects that just weren't cost effective to find with traditional ATE and test flows. And what's also interesting is over the last few years, as the rest of the industry has moved to these later, smaller process nodes, the automotive industry and even the consumer industry has started to adopt these additional SLT test flows. And if you really think about it from a test perspective, everyone really has been developing and optimizing manufacturing test flows based on what's the most cost-effective way to catch the defects, to replicate what these parts do at the system level. So if you can't catch these defects with that lower cost production test flow, then you have to revert back to the system level test to find those defects and then figure out if it's more cost effective to keep it at system level test or to put the work and effort into trying to replicate those faults earlier on in the manufacturing process. And that really is determined by the yield and the cost trade-offs in terms of the economics around those decisions. So the point I want people to take from this slide is system level test isn't new. It's been adopted and it's been mainstream now for over a decade, and now more and more verticals are beginning to embrace this as part of the standard test flow. So really the next step in the overall SLT isn't just the deployment of SLT, it's how can we now take what's in place and further optimize the economics around test to take further advantage of that new ecosystem, which is what we're calling Test 2.0. So if we look at it from a test flow perspective, the top is where we were a decade or so ago. People were taking sampling testing, and some people were adopting 100% system level test. And to a certain extent, this is still happening, but more and more people have fully embraced and adopted system level test 100% on their parts now. Some people still do statistical analysis based on small sample sizes, but more and more people are embracing system level tests. So that really takes us to the new paradigm shift, which is what we see on the bottom here, where none of the traditional test flows are going to go away. It's just where do you put the emphasis on how much system level test you do and how much do you drive back earlier in the process. And I know there's been lots of papers and debates around should you shift right or should you shift left. And I think, from a test perspective, we all want to catch these defects as early in the manufacturing process as possible, but sometimes it's just not cost effective to do that. So where it makes sense, people will shift left and do what they can and wait for test. But if you have to have system level test because it's the only way you can find some of these mission critical defects, then you have to embrace a system level test environment, as a lot of people are doing now. And therefore, in some cases, it makes sense to shift more of the testing to the right, where you can take advantage of the infrastructure that's already in place at system level test to also catch and test some of the test flows that you would normally do at traditional ATE that maybe rarely fail, but you still need to collect that data. And therefore, the time overhead of doing that in the system level test environment is actually more cost effective than doing it in a traditional ATE flow. But that only works on mature parts with good high yields. So that's the current test flow changes that we're seeing. On the bottom here, the move to system level test, and now the decision tree of whether to shift more left or shift more right. And those decision trees are being done now, taking advantage of some of those data collection and analytics that I mentioned on the first slide. So if we now look at the system level test ecosystem from an enablement perspective, there's people have been doing and will continue to do lab-based small sample testing where they need engineering debug, they need to test a small number of parts to get their process, their devices validated, characterized, and take that data to optimize the standard test flows. And then depending on the adoption of the system level test, the work that's done in the engineering environment, you also really want to do in a way that can scale into higher parallelism should you need to deploy it in production. And there's various methods that people are adopting to do this. So some people are doing just very much taking application development boards and socketing them in their engineering environment, adding in the thermal management to do engineering hand tests. Some people are then taking that and adding some engineering handlers to those engineering solutions. And then some people are then taking that and enabling them into higher parallel solutions that can then be taken and scaled from engineering into the high volume production. And yet again, in high volume production, there isn't a one size fits all, because it really depends on the test times, the package sizes, the yields, and volumes that will really determine the level of parallelism that people want to so what we see in the manufacturing area is system level testers that can take existing engineering size and big OEM application boards and put automation around them, which is a typical linear handler, such as this by 12 SLT handler that I've shown on the bottom left of the right circle. And then some people then take that and then further do the work to allow much, much higher levels of parallelism with these big system level test handling solutions that can handle hundreds of parts in parallel. As these test times are longer, you do need much higher parallelism to optimize the throughput. So there isn't a one size fits all, but there is a range of system level test handling solutions now available with thermal management and interfacing that can scale from small volume engineering solutions all the way into high volume production solutions if it's properly planned out as part of the test flow management. So moving on to the high level components of a high parallel system level test system. Most of these systems have some sort of JEDEC IO handling solution. At AEM, excuse me, at AEM, we manage the movement of parts directly from JEDEC in to JEDEC out. Other solutions do move loaded boards, more like a traditional burn-in solution, but in our solutions, we always have a JEDEC IO handling system. So you need software to control all of that. The transfer robot has to manage the movement of parts from the JEDEC IO handler into the main handler. There is then additional control for the test column. The test column is where you have multiple test cells. Within those handling systems, there's vision control and monitoring for making sure that you can recognize the right lots, the right parts, and make sure that the parts are properly handled throughout the handler and placed in and out of the sockets in a good quality manner, and look for defects in the socket in the interfacing and handling during the test process. So vision control is an important part of these handling systems. Test control and monitoring, I know there'll be some more presentations later on, but obviously the test program, the whole flow of the system level test within these handlers needs to be managed. We need to develop the test program, and we need tools to help debug the test program development. So we provide a full suite of test software to enable that, and thermal control and monitoring during the system level test, depending on the pattern activity will depend on the thermal requirements, and we need to be able to accurately control and monitor the temperature real time actively with the test patterns that are being run. So we have full thermal management that scales from the engineering bench all the way to a per site basis on these massively parallel handling solutions. So those are the major building blocks in a system. If we look at it from a software and test floor integration perspective, obviously these systems need to interface into the customer's host, the factory host, to download the right version of the programs, the right recipes, and then to collect and store the data. I think Jürgen mentioned earlier that you need data for 5 to 15 years in the automotive industry. All that data has to be downloaded from the system level testers and stored in the factory host environment. And then you need all the test floor monitoring tools in place to make sure the right parts are being tested with the right flows. So standard interface into customer factory host is an important part of the integration of these systems. And when you write even engineering level, system level test programs, it's worth considering this ecosystem to make sure that that flow is considered early on, rather than having to rewrite it when you go to these massively parallel test systems. But then from a test perspective, obviously you have some sort of master computer that interfaces into the factory host. You need the master computer to control all the automation in the handler. Typically you have additional vision computers for monitoring and managing all the vision that we talked about earlier. And then you have the test computers themselves, and these will vary depending on the system level test methodology that's being put in place. Some people have one computer that controls multiple system level test boards. Other people have individual computers that control per site within these systems. So yet again, it's not a one size fits all. It is a very semi-custom test flow at the moment, and it's very much dependent on the defects and amount of data that people are trying to collect in these system level testers in terms of what is the right test computer architecture. If we look at it from a very high level, there's some sort of high level computer. We call it an ACC, which is our AEM cell controller or test controller. You need a test controller, whether it's a PC or a dedicated test controller, to control the thermal management during test, and to provide the interface into the host computer, and also to provide all the standard interfaces for controlling the system level test boards in their native application environment. So typically a test board will have a socketed device, which is your DUT, and there'll be your native application hardware on the system level test board, and this native hardware will be the circuitry that replicates the customer's end application environment. And to control that, there's normally standard interfaces that are used during SLT, which consist of Ethernet, USB UART, SPI, JTAG, PCIe, and others. There's depending on the application, there could be HDMI and other types of buses that are also being used. But typically, there's some sort of standard interfaces that are controlled from a host computer or test computer for controlling these test boards. And the thermal management when running these tests. Also, at system level test, you really want individual power supply control per DUT so that you can manage a completely asynchronous test flow, so that if there are conditional flows for one DUT, you're not impacting or waiting for all the other DUTs to wait for one specific DUT. So these all set up typically to run completely asynchronously on these parallel handling solutions. So this is a very high level block diagram of a traditional SLT flow. Now if we move on and just to summarize where we are. Okay, right. So in summary, we've been through a lot of the items that are driving the need for system level test, the rise in power, the part complexity, the increasing in transistor count, the need for active thermal management whilst testing to manage the thermal behavior of the parts, the need for high levels of parallelism to handle the test times, and the intricacies of handling these complex parts. But if we also look at the left-hand side of this slide, another attribute that we'll see is the increasing amount of time it's taking at ATE to run DFT and scan on ATE for these increasing DFT circuits that are in these complex parts. And as we move to the newer process nodes, this is only getting worse with increased transistor counts. So the amount of time spent at ATE testing scan and BIST is continuing to increase. So if we look at it, system level test has been around for a long time now. It's been adopted by many verticals, and more verticals are beginning to adopt it as they need the extra faults coverage to capture faults that they can't traditionally capture cost effectively at ATE. So what we're now seeing is on the right hand side is, given the SLT is now part of the test flow for a lot of customers, it's now a matter of how can we utilize that flow and rethink the whole test flow and re-optimize based on test times, throughput, yield, and reliability trade-off. So what we are seeing is the continuous rethinking of the test flow from a shift left to wafer test to a shift right to system level test, and in the process which of the insertions between can be either sacrificed and or further optimized. So this whole rethinking of the back-end test flow we refer to as test 2.0. It is a paradigm shift, and it is the next step to try and optimize not just the faults coverage and reliability, but overall reduce the overall cost to test. And as a result of that, maybe some of these test flows that are being done on traditional ATE belong more at wafer test, and in other cases belong more at the system level test. If the yields are high enough, it makes sense to do a lot of these DFT flows in the back end at system level test. So this whole process is being rethought, and we'll look forward to working with the industry as we reshape the back end over the next period. So thanks everyone for your time, and I'll hand it over to Mike.
Send them to you afterwards, Stuart, and send those questions, those your answers back to the people who asked the questions. But thank you very much, Stuart. It's a very good overview of SLT and how it's been sort of integrated into the traditional test flow. It's very interesting.